Sachik Gelander. He's our next speaker. He's from the Weizmann Institute of Science at Rehovot, Israel. I have not had the benefit of knowing him in any detail, but one thing that appealed to me was that he is going to talk to us about a proof of a conjecture of Margulis that he has obtained in collaboration with. So the title of the talk, as you see on the screen, is Infinite Volume and Infinite Injectivity Radius. And it is joint work with Nikolai Fratsik. I think that's the pronunciation. Over to Dr. Gelander.
Thank you. So, okay, so I would like to thank the organizers for inviting me. It's exciting for me to speak in the conference for Raghunathan. Raghunathan was one of the mathematicians who mostly influenced me from far away. In the beginning of my PhD, I spent some time studying his book, which is now on the reading list of all my students, the book about discrete subgroups of Lie groups. And by the way, my students prefer his videos on YouTube, which were not available at my time. Among the Raghunathan work that influenced me is, one thing is that his work with Garland about fundamental groups, fundamental domains of rank 1 lattices. Of course, his celebrated work on the congruent subgroup property, and also his work with Moses and Lubotsky. This is about the geometry of high rank non-uniform lattices and the distortion of unipotent element, which is one of my favorite theorems about the geometry of lattices. And many other work of Raghunathan's. So my talk is about, the title is Infinite Volume and Infinite Injectivity Radius, and it's a joint work with Nikolai Fratsik. And we prove the following theorem. So I hope my internet is good. So let G be a simple Lie group. I will state it for simple rather than semi-simple. Maybe later on I will discuss semi-simple group. It's more convenient to assume that for simplicity. Of rank, real rank, at least 2. And let lambda inside G be a discrete subgroup. I use lambda because usually I use gamma for lattices, and here I don't want lambda to be necessarily a lattice. Then the locally symmetric space G mod K, I take the same notation as Shachar, mod lambda, maybe switching orders, as infinite volume. If and only if it has infinite injectivity radius. So it admits injected, contractible balls of any radius. Yes, so this was conjecture by Margulis, and so basically you should think of a manifold of or orbifold of infinite volume. So it has some geometry, but if it has infinite volume, then at any point you can find, or not at any point, for any radius, you can find somewhere an injected contractible ball with that radius. So basically, this is a result about general discrete groups, and mostly about non-lattices. I think by today we have there is a remarkable theory about lattices, but there are not so many results about general discrete groups. But this can also be realized as a result about lattices, because it says that it's characterization of lattices. Basically, the volume is finite if and only if the injectivity radius is bounded. So by the way, Margulis has a wonderful proof for the Borel-Arishandra theorem that arithmetic groups have finite volume. And when I think about this proof, I think of it in two steps. So it proves like a criterion. So if you have a locally symmetric manifold, and it has a property that when you go to infinity, the injectivity radius go to 0, then the volume must be finite. And then it shows that the arithmetic group satisfy this. So here you can say you don't need the injectivity radius to go to 0. It's enough even that it's bounded, and then it implies finite volume. But this is only for higher rank. So maybe I will write an example. So let G be of rank 1 now, like SON1 or SPN1 or etc. And let gamma in G be a uniform lattice. Let lambda be a normal subgroup in gamma, non-trivial, of infinite index. So gamma is a hyperbolic group, Gromov hyperbolic group, so it has many normal subgroups. So you can find in particular a normal subgroup of infinite index. Then the manifold G mod K mod lambda has infinite volume, but bounded injectivity radius. And how do you see that? Consider, okay, so let omega be in the symmetric space compact, such that it's a fundamental domain. So if you want, gamma times omega covers the symmetric space. So I assume that gamma is a uniform lattice. And then let D, or let's take some element, let alpha be an element in lambda. And D be the maximum of the displacement of alpha. This is the Riemannian distance, and this is how how the group acts over this compact set. So this is a finite constant. So now for every y in the symmetric space, let gamma in gamma be such that gamma inverse y is inside the fundamental domain. And then you see that D of gamma alpha gamma inverse, the displacement at y of this element is the same as the displacement of alpha gamma inverse y, gamma inverse y, and this is in the fundamental domain. So this is at most D, and this element is inside lambda because lambda is a normal subgroup. So you see that in that way you get a manifold of infinite volume, but bounded injectivity radius. So the theorem has several applications. So in particular, it implies Margulis normal subgroup theorem that if you have lattice in higher rank, then every normal subgroup is either of finite index or central. But it says much more. It says things about general, not just normal, but any subgroup. And it also says things about discrete group which are not in a lattice. But again, it is only, Margulis proved his normal subgroup theorem in a greater generality, for instance, in SL2R times SL2R for reducible lattices. And we do not know to prove our theorem. So we need some stronger assumption. But for when this assumption applies, like for instance, if G is a product of higher rank groups, then it implies a stronger statement. It also implies the result of the 7 authors. A few years ago was a paper by Abert, Bergeron, Biringer, myself, Nikolov, Rambald, and Samet, and we proved the following theorem. So again, let rank G be at least 2. Then for every V, or for every R, there is V such that if the volume of the locally symmetric space G mod K mod gamma is bigger than V, but finite, then G mod K mod gamma admits a point of injectivity radius at least R. Yes. So if you have a large volume, then you have a large injectivity radius, but in that work, we assumed also that the volume is finite. All the methods were using lattices, theory of lattices, and now you can delete this assumption. So whenever the volume is big enough, even if it's infinite, then you have large injectivity radius. And the proof is using random walk, so it uses probabilistic method. Basically, we show that we want to show that the R thick part is non-empty, and we show that if you do a random walk on the locally symmetric manifold, then you will spend eventually most of the time in the R thick part, and this is true for every R. So let me introduce some more notation. And we actually don't need to speak about manifold. We can discuss it all inside G. But so definition, lambda and discrete subgroup of G is called uniformly slim if the orbifold G mod K mod lambda has bounded injectivity radius. So that's uniformly slim. It means, okay. And the result, the theorem that we proved is that for higher rank simple group, to be uniformly slim is equivalent to be a lattice. Now, this is equivalent to the following. So there exists C inside G compact such that C intersect every conjugate of gamma, of lambda, non-trivially. And if you want, lambda is not uniformly slim if and only if there is a sequence Gn in G such that the conjugation of lambda by Gn converge to the trivial group with respect to the Chabuti topology, the topology of closed subgroups. So yeah, topology of closed subgroup, I mean the Chabuti topology. So that's uniformly slim. And to say something about the proof, we look at random walks on the space of discrete subgroups. So there is some philosophical sentence that I like to say, that in mathematics, it is fruitful to add randomness, and indeed, sometimes we are able to prove results about random objects which we cannot see about a deterministic object. But it seems like a miracle sometimes when we can say something about a deterministic object by viewing them as random object. Now, in the last 10 years, the theory of invariant random subgroup was very fruitful, and many results about asymptotic invariant of lattices was proved using the notion of invariant random subgroups. However, when you consider non-amenable group, to restrict yourself to invariant probability measure, it's a big compromise. So this is what we did here. We allowed ourselves to deal with with a more general notion, which is that of stationary random subgroup, and the stationary measure is what you get by looking at the limit of a random walk. So let mu be a probability measure on G. By the way, so G, or before that, I look at sub G is the Chabati space of all closed subgroup of G. This is a compact space. And inside we have the subset of discrete subgroups. Which is an open subset of sub G, because we discuss real Lie groups, so there are no small subgroups, so it means that sub D G is open, and G acts on this space by conjugation, and by random subgroup we mean some probability measure on this space. And the invariant random subgroup is a probability measure which is invariant under the G action. And now I want to consider a more general notion of stationary random subgroup. So mu, this measure mu is a measure on G, and explicitly mu I will take this measure, where this is a Haar measure on the maximal compact. We fix a maximal compact subgroup, and Dirac measure on S, where S is some semi-simple element, a semi-simple element which expands a lot when acting on the unipotent radical of some minimal parabolic. So basically, just example, you can take S for SLN to be a diagonal element as long as you have big jumps, big enough jumps for every I. So that's a measure we will work with inside G, and then given lambda, which is a discrete subgroup of G, so it's a point in the space of discrete subgroup, consider the random walk. So we do convolution. We start with the point at that point, so we start with the Dirac mass at that point, and then we look at the Chazaro average, and let's call this nu n. So that's a probability measure on the space of discrete subgroup of G. And then the theorem that we proved the theorem by Miko Y. Fakchik and myself is that under the same assumption that G is rank 1 simple group, this nu n converge to the Dirac mass of the trivial group. Now you see that if you start with the element, so all this nu n, all these measures here along the way are supported on the conjugacy class of lambda. So the limiting measure must be supported on the closure of the conjugacy class. And therefore, by showing that it's this, in particular, it would mean that lambda is not uniformly slim. So again, so maybe I will state the theorem precisely because so the theorem says that if rank G is at least 2, and let's say G is simple, there is a version also when it's not simple, but and lambda inside G discrete, but not a lattice, then we have this. And so that's a theorem. And let me say something about the proof. The proof has 3 steps. Step 1 is to prove discreteness. So you see the space of discrete subgroup is open in the space of all closed subgroup, but it's not closed. So you need to show that the limit is discrete. So we prove the following theorem that if nu infinity is a limit of nu n, a weak star limit, then it is supported on discrete subgroup. Nu infinity of the space of this open set is 1. So almost surely, if you take a random group, it will be discrete. And this result made use of a recent work by a recent joint work by Ariel Levitt, Margulis, and myself. And what we actually studied a quantitative version of the celebrated Kashdan-Margulis theorem, a concrete quantitative version of that. This paper was submitted to the special volume for Prasad 75th birthday, but the main result there, the main technical result is the following theorem that we proved. There exists some constant delta, some constant C, and some constant B, such that, I must introduce a notion, sorry. You want to define the discreteness function. So let this be a norm on the Lie algebra such that the exponent is a diffeomorphism when restricting to the unit pole in the Lie algebra. Then define the discreteness function for a discrete group lambda to be the supermum of R such that the exponent of the ball of radius R intersect lambda trivially. So that's measure how discrete is the group lambda. But it doesn't see large injectivity radius, only small injectivity radius. So that's the weakness of this is that it only see small injectivity radius. But the strength of this is that you can prove for the measure I defined above that for every lambda in G discrete, the convolution of I to the minus delta of lambda is smaller than C times I to the minus delta plus B. And basically, if you know that, then you can argue, like in the paper of, like in the work of Margulis and Eskin about random walk on G-mod gamma, and prove theorem 1. So for the work here, we just need these constants, but for the work with Margulis and Aryeh Levitt, we wanted the explicit constant. Here we just needed it to be less than 1, and there we wanted something very effective depending on G. So this is step 1. Step 2 is stiffness result. Basically, we prove the following theorem. A discrete, stationary random subgroup is invariant. If you want discrete SRS, that's the new notation, implies IRS. And this result, so this limit measure, it's a limit of Chejaro average of convolution with mu. So the limit will be mu invariant. So will be mu stationary, and therefore it must be actually invariant. That's the result, and this relies heavily on the remarkable work of remarkable work or works actually, because it's a series of papers of Rehovot and Zimmer. So there is Rehovot and Zimmer extended Margulis factor theorem to stationary action of semi-simple high rank group, and we relied on that. And the last step, for our consideration is rigidity, and here we apply Stuck-Zimmer theorem. So in the general high rank case, when we allow semi-simple and not simple, there is something to prove. But here, when you deal with the in the simple case, so it's once you have an IRS which is supported on discrete group, then you know that it's support either on the trivial group or on lattices. So if you apply Stuck-Zimmer theorem plus local rigidity, then you get that if the original group was not a lattice, So in the limit of the conjugacy class, you cannot have lattices, and therefore the stationary random subgroup must be supported on the trivial group. So I think that's my time to finish, or I have more time. I'm a bit confused about the time. I don't hear you. Danny, you are muted.
Yeah, officially the time is finished, but you might take some time to wind up if you wrap up.
Maybe I'll say some. I'll just write one theorem in the general semi-simple group. So because I restricted to simple case, so it will take half minute. So theorem in general. So let G be a semi-simple Lie group with no compact factors, and let lambda inside G discrete such that lambda intersection with H is not a lattice in H for every H which is not trivial and normal in G, then for every limit of this Chazaro average mu I convolution, if you do the random walk, is supported on discrete subgroup of the product of rank 1 factor of G. So that's somehow a general result, which implies some consequence in this. So you have some rigidity. You don't see the high rank factors in the limit, only rank 1 factor, but there could be interesting measures supported on discrete subgroup of rank 1 factor. This was, you can actually construct non-invariant stationary random subgroups on rank 1 groups. Okay, yeah, maybe question.
Thank you, Dr. Gelander, for the talk. Now, are there any questions? Raghunathan? No. Okay.
I just want to ask one question, which is a simple question. Professor Gelander said that a set of discrete subgroups is open in sub G. So that's for semi-simple group G. Is that what?
That's for every Lie group. This follows when you have no small subgroups. So there is this notion of non-small subgroups. So G has no small subgroup if there is an identity neighborhood which contains no non-trivial subgroup, and this is equivalent to being a Lie group actually by the Hilbert-Thief problem. So for every Lie group, the set of discrete subgroups is open in the space of all subgroups. You don't need semi-simple.
So nothing from outside can converge to discrete subgroup. That's what it means.
Yeah.
Oh, thank you very much.
Any other questions? There are no questions. Let's thank Dr. Gelander once again for the talk, interesting talk.
Thank you.
Thank you. And with that, I think we will have I declare this session closed.